Well, hi, Adam. Thanks very much for joining us today to tell us about your research. I know you're joining us from rural Ireland today, so hopefully our internet connection will hold up. Before we start talking about your research, I have a few icebreaker questions that I wanted to ask you so we can get to know you a little bit better. Can you tell us what would you have been if you hadn't been involved in medicine and research?
That's a good question. I suppose thinking back, my earliest memories when people would ask me this question, I used to say I wanted to be a professor or president of Ireland. So I used to equate the two. I used to think they were very similar. So I guess the ship hasn't sailed on president of Ireland yet, but let's think professor might be more achievable in the medium term.
Well, big ambitions either way. That's good to see. Can you tell us something that you're either really good at or something you're really bad at?
I'm sure my wife will tell you that my sense of direction is the worst in the world. So if it wasn't for Google Maps, we would have had problems in our relationship.
I guess that will be something that a lot of people can relate to, I think, in our audience. What's your favorite place in the world?
Actually, I have to say rural Ireland at the moment is certainly my favorite place. I live in central London. I'm working at Imperial College. So it's very busy and space is at a premium during a pandemic. So to get a little break and come to Ireland seems like a big treat now. So green fields as far as the eye can see is quite nice for the moment. I'm not sure I could put up with it long term, but right now, rural Ireland is great.
Excellent. Sounds like a good balance. Now we'll move on to talk about your research and the research study that ASME UK and the British Lung Foundation are funding. So first of all, can you tell us about idiopathic pulmonary fibrosis? So what is it? How common is it? How does it affect people?
It's a terrible disease. It's very poor survival rates. It's a disease of the lungs, where the lungs essentially become scarred. So what you want in the lung is very thin barrier between the blood, where the oxygen gets delivered to, and the lungs. What happens in IPF is that a wound healing takes place. So maybe in your skin, that's a good thing. But when you have a wound in your skin, you can see this kind of thickened tissue that's left behind. In the lung, that's a bad thing because it makes it difficult for oxygen to get into the blood. So it makes it difficult to breathe. So it's relatively rare, but there's increasing incidence. But one of the major issues with IPF is that there aren't any therapies. So currently the average survival is about 3 to 5 years. And the drugs that are available for IPF, they just slow the decline of lung function, but they don't reverse it. So it's really, really important that we understand the mechanisms involved. Like, how does this happen? Why do the lungs react in that way? And once we understand that, then we can start thinking about, ways to reverse that.
Your study, which ASME UK and the British Lung Foundation are supporting, is looking at a substance that's found naturally in the lungs that you think could hold the key to stopping this lung scarring. And can you tell us a bit more about that?
So what I'm really interested in is the immune cells in the airways and in the lungs, and how they are changed during IPF. And there's been work ongoing in different diseases, completely unrelated, which have found that a particular cell that I'm interested in, called macrophages, which defend the lung. And what's really important for their function is their metabolism. So they need energy to be able to do their functions. So whether it's to cause wound healing or whether it's to protect the lungs. So how they process energy is really important. And what happens when you are producing energy is you produce metabolites. So these cells start to produce metabolites, naturally occurring substances. And it turns out those substances aren't only for generating energy. They've evolved with the immune system, and they actually can have pro-inflammatory roles or anti-inflammatory roles. And there's been a lot of interest in one particular metabolite, which is called itaconate. So it's a byproduct of metabolism. And it turns out it's anti-inflammatory. So I was really interested to see whether this molecule was around in IPF lungs and what it did during IPF. How was it involved in the process? I was able to get some samples from IPF patients from washings of the lungs. And basically I measured how much itaconate was in those lungs, and it turns out it was gone. So in healthy lungs, there was itaconate in the lungs, and I think it's there to protect the airways, but in IPF it's missing. So we said, okay, what's going on there? So we did some work and teased out what was going on. And it turns out itaconate might be an antifibrotic that's naturally occurring in the lungs that's missing in IPF. We wonder if we can put it back, and maybe it can begin to resolve that lung fibrosis.
I mean, that sounds amazing. You know, not least the fact that this is a naturally occurring substance in the lung. It's not something that is, you know, foreign or a manufactured molecule. This could be something that could be well tolerated in the lungs. And if we know that it's missing in people with IPF, yeah, it would be very interesting to see what would happen if it was put back in. And am I right in understanding that you're hoping to potentially alter the chemical structure of this substance to see if that would make it even better at stopping the lung scarring?
We want to understand how much we can put into a lung, you know, because, you know, it's not the perfect molecule maybe as a drug, because it's it's endogenous, you know, it's just there kicking around in relatively small amounts. And we wonder, can we put it back in? How much can we put it back? How much can we put back in? But the other thing is, can we weaponize it? Can we slightly change its chemical structure so it's still safe, but it gets into the cells much quicker, so we don't have to put, or better, it gets into the cells better, so we don't have to put too much in. So it's kind of a balancing act. And one of the really important things is we've discovered it. We can see that it's anti-fibrotic. If we put it on cells from IPF patients, it dampens down the fibrosis. But what's really important is exactly how does that work? You know, what are the nuts and bolts of how itaconate can stop fibrosis?
And do we have any idea about why itaconate might be missing in people who have IPF?
Yeah, so that's a really big question. So I've been looking into that. You know, is there environmental? It could be an environmental pressure, because we know that IPF, the environment is very important. Pollution, smoking, things like this. Is there any of those factors that might dampen down the itaconate? We've investigated whether it could be genetic. Is it something that could be inherited? So we've established collaborations to look at that, and it doesn't seem to be that either. So there's an ongoing kind of study that's part of what we want to do. But I think it might be part of the immune system. I think other parts of the immune system might be dampening down that itaconate. That's my current working theory at the moment. So as part of this project, we're going to be teasing that out also.
And I guess, you know, the final question really is, you know, what do you think your research could ultimately mean for people with IPF? And how quickly do you think this might make a difference for those people?
The first thing is, I know we want to go straight to therapies, right? That's the answer everybody wants, and that's the answer I want. But first, I think it's a fundamental understanding of how the lungs operate during lung fibrosis. That's the first thing that's going to give. I mean, those cells that I mentioned, the macrophages, we know they're really important. And there's loads of aspects of how macrophages behave outside of metabolism. So we really want to understand what they're doing during the disease. So we don't come up with a drug. The next person will have more information to be able to do that. But my real hope is that maybe itaconate or modifications of itaconate could actually make it to the clinic. Last part of the puzzle we want to do in this project, and this is a 3-year project, will be to actually take slices of human lungs. So we can get lungs from during surgery when bits of lungs are from a biopsy, essentially. And we can slice them really thinly and we can keep them alive in the lab. So actually what we're going to do is try to make those fibrotic, put itaconate on top and see if it can stop that. So it's as close as we can get before a clinical trial to actually looking at how itaconate behaves in human lungs. And one of the ways that, or one of the reasons that a lot of therapies kind of fall by the wayside is because they're not being tested in very relevant systems. If we can get to that stage and we have a new candidate, whether itaconate or a modification of itaconate, that could move on to preclinical testing. Okay, so I'm interested in lungs and how they work. And in particular, I'm interested in lung disease. So when people get sick because their lungs aren't working the way they should. And what happens in the disease that I'm interested in is when lungs become thicker. And that makes it very difficult to breathe, because when you breathe in, oxygen needs to get into your blood. And then when lungs become thicker in this particular disease, it's very difficult for oxygen to get into the blood. So this disease is called idiopathic pulmonary fibrosis, or IPF for short. So what I want to understand is how does the lungs defenses get broken during IPF? How can we fix that? And one particular way I think we can fix that is to use products or metabolites from the immune system and to put them back into the lung. So these are beneficial metabolites that we found that potentially could reverse lung fibrosis to make people who are very sick a little bit better.
Well, thanks so much, Adam. Thanks for spending some time with us and talking to us about your research. I hope everything goes really well, and I'm really excited to see how it all turns out in about 3 years' time. So yeah, good luck and thanks again.
Thank you.